Well, welcome to the July meeting of the Columbus Astronomical Society. I'm Charles Losco, president. We're going to get started here. I guess our first announcement about CAS is, sir.
Yes, thank you.
Thank you, Charles.
So good evening, everyone. Welcome to the Columbus Astronomical Society. My name is Isaac Cruz. I am the lead for CAS, which is the Columbus Astronomical Society Imaging and Special Interest Group. And basically what I do is I take pictures of the sky. We're just talking about, the things that that I love to do, and one of them is to point the camera to deep space objects and image them. And if you're interested in that, we invite you to actually to come over to our meetings, which are in this venue right here on the third Saturday of the month. Now, this month we will not have a CASIS meeting, but we'll have one in August. Okay? So don't despair; it's okay. We have the director of the Perkins Observatory will tell you a little bit about it, but we want to make sure we don't have conflicts with the programs that are presented here in Perkins. So this month we will not have one, but if you are interested on imaging what's in the skies, come over to the Perkins third Saturday of August, and we'll talk about it. If you have any questions at the end of the meeting, look me up, and we can talk. Thank you very much. Appreciate it. Have a good night.
Yes. Okay, I'm Joe Stark. I'm the outreach coordinator and also the creator. We have three guests with us this morning, or now this evening.
Really early morning.
Really early morning.
Somewhere.
Federico. Where's Federico?
Right now.
Federico. Yes.
Hello.
Raise your hand if you.
Just thanks, everybody.
Another visitors. Dana. Is back there. And Lawrence is right here. So, welcome. The other thing is that we have a couple of things coming up that I need some help with. One of them is coming up rather quickly, the 25th of July, Friday evening, just down the road here at Deer Haven Park. It's a sign-up sheet for telescope viewing. If you are able to re-scope and would like to do it, help us out, I'm going to pass this around. There are 2 pages. So in case you fill out one page, there's another page, okay? I'm just kind of planning that here. The other thing is something that's coming up not until October. October 11th actually is a daytime event, 11 a.m. to 3 p.m. at Slate Run Metro Park in Canal, Winchester. I was just asked if we would be interested in having a booth there. If no one signs up, I'll tell them we don't have any interest. But if you are interested at all, sign up, and we'll let them know that we have some people who will have a booth, calling us, telling people about the club. You could possibly even bring a solar scope if you wanted to do a solar scope viewing. Okay? So I'll pass these out. I'm going to do one on this side and one on this side. Through that switch sides, popping out at the end of the row, so we can give everybody a chance to sign back. Okay? Okay, thank you.
Okay. So next month is the club fall event. So we'll be having food. We may or may not be viewing. You never know how the weather's going to go. But think about your favorite food, bring something, and club will provide some things too. So it's usually a good time. Ask questions about astronomy or whatever. We don't have something settled for October right now. I know. You don't know. No. Okay. We'll have to announce that whoever is speaker is going to be in October. But for now, I guess we'll have a word from our host, the director here at the observatory, and he's going to do our presentation for general relativity. So, few words, we'll carry on.
As in many clubs like this, people wear many hats, and I do as well, just for here, university and that. But yes, I am the director of Perkins Observatory, and we are, first thing I'd say is going to start resuming our public programs, because, of course, an incident early in the year, a major leak and problems on our basement with flooding. Got most of that cleaned up and some of the damage taken care of, but we still got a lot more work to do. So unfortunately, we are still limited to the single-fuse truss up here on the first level to the other side of the wall here. So I do appreciate patience on that. I have no idea though when we're going to get an island restroom running yet, so that might take some time. I'm making everything else so we get that taken care of. On the public programs, we're starting next Saturday with our Celebration of the Sun programs. These are 2 Saturday afternoon programs from 2 to 4 p.m. about the sun. And I like to have folks come. If you have a solar telescope and stuff, if you don't, know a couple here at the observatory. It's a lot of fun to have folks in the public here and show them the sun. And it's something rare that people can do safely. And that's what we do. And there'll be a little talk consisting of our knowledge about the sun, what it is, what it does for us, and we'll tour the observatory. And for the kids, I'll do a little rocket launch demo. Those will love that. And so that's going to be next 2 Saturdays from 2 to 4 p.m., 19th on 6th. August 1st, we will resume our Friday night programs. And because of the restroom situation on these programs, I'm limiting the guests to about 20 people per program. But still, I think as many of you come volunteer as you can, and it's very helpful and appreciated for these programs. And if that happens to be clear, of course, let's telescope out there and show folks the moon, double stars, and other bright objects up there. It's typically a good time for the public. But for now, unfortunately, like I said, because the situation will limit the number of guests that we have, so the program is going to be a little bit smaller and intimate. So this will also be a good way to kind of get your feet wet and, where you're not overwhelmed by a large crowd or anything like that. They have a program down Jacob, and a lot of people down there. We used to have people close to 60 people. Our program, that's about time being or something, we about 20-something guys. I'll post on the CS unless, the particular night needs some help. If it's cloudy night, I typically don't post, I don't want folks traveling up here and not have anything to do. But definitely on those clear nights, if you're looking for something to do on Friday night, bring your scope up. You don't have to be an expert. You don't have to have a telescope. Because I've got a few telescopes around that you can use as well. People are ready to grab one of the club water scopes that are trying to light. Okay? So without further ado, I guess I'll put my other hat on. I guess I'm your speaker tonight, and I'm going to spend a little time. This is almost like a follow-up talk to, and then earlier this year, Brad Haynes' talk on special relativity. We'll be putting some of his talk in this, but it's going to be focused on general relativity. So without further ado, I'll get these lights down. Hopefully everyone can see the screen clearly. I'm going to cheat here using some notes and stuff like that, so it's why I do that. I'll start with basically there's a lot of mythology and misunderstanding about surrounding Einstein and the special and general theories of relativity. Though Einstein was no doubt a genius, his theories did not arise out of a vacuum. His ideas were built upon the work of others. These other great physicists, mathematicians, often received very little acknowledgement for their contributions. Without their work and insight, Einstein may have remained in aluminum patent cord for the rest of his life. Einstein, like Newton, stood on the shoulders of giants. What I will emphasize will be the important physics and mathematics that forms the backbone of the general theory of relativity in the historical context. This talk is by no means a complete history of the topic. I'll gloss over some things in favor of others. There'll be some hand waving as well. Finally, if there's time, I will look at one of the most profound and recent confirmations of his general theory of gravitational waves. So we'll start our journey in 1933 at a Christmas dinner held at Trinity College in Cambridge. At a particular table sat noted physicist Ernest Rutherford, atomic physicist, discovered the atomic nucleus. Sir Arthur Eddington, a noted astrophysicist, he helped develop the stellar nuclear synthesis model. Chandra Shekar, another noted astrophysicist, he did important work on white dwarfs and thermodynamics stars. Sir Maurice Amos, lawyer, judge, and legal scholar. And finally, Patrick Duval, a noted mathematician at the time. This table I would have liked to sit at. In the course of the evening, the conversation turned to Einstein. Amos turns to Rutherford and says, I don't see why Einstein is accorded more public acclaim than you. After all, you invented the nuclear model of the atom, and that model provides the basis for all of physical science today, and is even more universal in its application than Newton's laws of gravitation. Whereas, granted that Einstein's theory is right, I cannot say otherwise in the presence of Eddington here, Einstein's predictions referred to such a minute departure from the Newtonian theory that I do not see what all the fuss is about. Rutherford turned to Eddington and said, you are responsible for his fame. Let's see what all the fuss is about. And if Einstein really was due, the fame accorded him. So we'll start with our journey, we'll go further back in time to actually the first theory of relativity. Indeed, the concept of relativity does predate Einstein's. Most thinkers at the time held an Aristotelian worldview. Aristotle, who was a 2nd century BC philosopher, thought that something is moving because something is making it move. Objects fall to the earth because they are compelled to be near the earth. They fall towards the center of the universe. This led to questions, though. How do you explain the perpetual motion of the planets? Now, Kepler here said, I don't know, maybe it's the angels of the motion. The beginnings of an answer started to come together with Galileo and his theory of relativity. Galilean relativity is demonstrated by a thought experiment that he put forward. We'll update it a bit. So we'll consider a windowless ship traveling at constant velocity on a smooth ocean. Now imagine two people inside the ship playing tennis. As the ship sails along, Galileo states that the tennis players will not know they are in motion. In other words, the laws of motion are the same for all observers. But still, there are unanswered questions about the emissions of planets that separate answer them. These questions didn't begin to get answered until this guy came along. It's quiz time. About Newton's laws of motion here. Who can tell me Newton's first law of motion?
Who can tell me? Go out and stick. An object in motion stays in motion unless otherwise acted.
Yes, also known as law of inertia. Very good. How about the second law?
Action reaction. That thing. No. Then it like.
It's a mathematical expression of what that force is. It talks about the first law, F equals a. What you're referring to is the third law. Okay. So let's look closely at the first laws, because it is an absolutely revolutionary statement, probably the most revolutionary statement in all of physics. Because basically it says velocity is something that is persistent without cause. You don't need to explain motion. You only need to explain acceleration.
Me.
So in other words, no need for angles.
Deeper. This. What?
Now, when formulating his laws of motion, Newton introduced what are called inertial observers. Okay, an inertial observer is an observer that's at rest with respect to an inertial frame. In other words, without acceleration. That's what that means. So, in other words, Newton's laws of motion must be valid for all initial observers. Like here for this experiment done by the Mythbusters many years ago. They fired a cannon at 60 miles an hour as they were traveling at 60 miles an hour. As you can see, the laws of motion are hitting. The ball drops straight down. So we jump ahead to 1905 when you meet a young Einstein. Not that young Einstein. No, not young Frankenstein.
That's Perkins.
I'm sorry. Yes, that young Einstein. He had issues with some of Newton's assumptions and formulation of relativity. In particular, the dependence on dynamical experiments, among other things. Newton appealed to experiment to formulate his ideas. Einstein believed that experiment should appeal to theory.
Don't we see this?
So Einstein had a couple of options.
Yeah, that's the other.
First, dismiss Newton relativity altogether,
Daddy.
or remove the restriction of mechanics. He chose the latter.
Don't.
So, Einstein modified Newtonian relativity, and he did it as follows. All the laws of physics are invariant under a transformation from one inertial frame to another. In other words, the laws of physics are the same, regardless of which inertial frame you observe from.
It's good.
He had other problems with ideas, though. In other words, he didn't stop things.
Okay.
Other assumptions made by Newton when he formulated his laws. Newton said there was an absolute space, absolute frame of reference. Time is absolute. Everyone basically observed at the same time.
Good.
There's no fastest velocity. This could lead to things like instantaneous action at a distance. Simultaneity, that everyone sees the same thing, regardless of whether they are happening at the same time. And then finally, this principle, Newton's principle of equivalence, and we'll go more into what this is later. So, we need to look back also at the work of James Clerk Maxwell in his work in electricity and magnetism. Maxwell's work laid the foundation for the modern age. He found that light was an electromagnetic phenomenon. In other words, he connected light, electricity, and magnetism into a unified theory. Quite revolutionary. Now, contradictions would arise with Maxwell's equations, such as when they are used in cases of high velocity, things traveling very fast. And this bothered physicists at the time, and Einstein took a serious issue with it as well. Key clue was when Maxwell showed that all electromagnetic radiation travels at a constant velocity, the speed of light. And he derived this from his equations of electricity and magnetism. Now, many of you recall or have since watched Brad's talk on special relativity. I got another quiz for you. What is special relativity to you? How would you define special relativity? Anybody? Be shy. In the trial?
Relativity in the absence of gravity.
Okay. Anything else? Well, here's a more modern definition of relativity. Under coordinate transformation, the space-time interval squared is a variant in the laws of physics might be observed. That's a lot to unpack there, and it contains a lot in it. Okay? So I'll go more into exactly what all this is later, like what is this space-time interval and what is its origin. The key point here is the laws of physics are obeyed by frames of reference. That was the important thing that Einstein demonstrated special relativity. So the consequences of this are manifold. So part of it comes from Einstein, the little thought experiment he had. Imagine if he was riding along with a beam of light. What would he observe? You realize there wouldn't be any consequences to this. One of the things he discovered is that these things called the lens transformations would be preserved. They would show up and they would correct some of the things that were observed in certain experiments at the time. These were derived by Henry Lorentz here. He formulated these in the 1800s, 1900s. These made Maxwell's equations invariant, right? They solved the problem. Another thing was principle, again, Brad talked about in his talk, is length contraction. All right, moving objects contract in the direction they move. Objects get shorter as they approach the speed of light. Things like that. He also found a new way to add velocities. You couldn't just add two velocities together willy-nilly, and because you would wind up with contradictory results in these velocities if you did not account for the effects of special relativity. Then he found this equation here, and it's important to note is that at very, very low velocities we deal with in everyday life, right, this term essentially becomes zero, and so this is basically the normal way you would add in Newton's laws, adding velocity. So it reduces to Newton's laws in everyday situations. Only when you're approaching the speed of light does the addition of velocities change. The other thing is clocks tick slower. Tick high velocities. Right? So a few around years ago, I gave a talk about an experiment I did involving a particle called muons. These are subatomic particles created by cosmic rays hitting our atmosphere and generating these muons. And they're very short-lived. They only live about 2 microseconds. We should not be able to detect them on the ground. However, because of the effects of time dilation and length contraction, these particles make it to the ground and we can detect them in detectors. And so there's no absolute time, in other words. And finally, gone was the concept of simultaneity, because we have to account for the fact light takes time to travel. All right, so not all observers are going to see the same thing because of the travel time of light. All this was part of what's been called Einstein's miracle year in 1905, where he published 4 papers, 4 groundbreaking papers. One paper, special relativity, involved his mass-energy relationship, E equals mc squared. Another was for the photoelectric effect. You know, a lot of technology is based on that now. Automatic doors, things of that nature. And the Brownian motion, which is basically random motions of particles, that showed that matter is quantized into little things called molecules. Okay? So, pretty productive year for him. Einstein didn't return to relativity though for two years until 1907.
Yeah.
And so in late 1907, there was this conference in Germany. And that's where we introduced the next player in our story here. This guy here, Hermann Minkowski. All right, he was actually one of Einstein's professors when Einstein was attending university. Minkowski and Einstein actually had a very strained relationship. Einstein did not do well in his academic studies. And he annoyed Minkowski, and Minkowski often referred to Einstein as a lazy dog. However, he had read Einstein's paper on special relativity, and he recognized its importance. And at this conference, he decided to present his ideas based on Einstein's paper on special relativity. His opening statement at the conference was, "The views of space and time, which I wish to lay before you, have sprung from the soil of experiment, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade into mere shadow. And only a kind of union of the two will preserve independent reality." In other words, he proposed the unification of space and time. So let's look at this Minkowski space-time. So let's recall Euclidean geometry. This is geometry most of us learned in junior high and high school. Okay? Basically a collection of points forms a geometric plane in 2 dimensions or volume in 3 dimensions. Pythagorean theorem, the sum of the sides or the angles of a triangle are 180 degrees, think all that stuff. All right, that's all Euclidean geometry. What Minkowski introduced was by introducing time as you have another coordinate in the system. Instead of having geometric points, he called them events because they had a finite time they occur. Right. So there's basically 3 spatial coordinates and a coordinate time now. And it's what's called a fictitious coordinate space. Now here, fictitious does not mean fake. It means a theoretical framework. He defines what we now call a space-time continuum, what includes the past, present, and future. And he basically formed a once-and-for-all picture of the world that describes everything as geometrical structures within space-time. He introduced the concept of the space-time interval, which I mentioned earlier. And it's basically the interval between 2 separate events in space-time. It is given by this equation, which we call the space-time interval. And what makes it powerful is that the space-time interval is the same for all observers. It's invariant, as we'd say in physics. Now, this is not Euclidean. Why is it not Euclidean? What makes it different than Euclidean geometry is the minus sign here. This is called pseudo-Euclidean. Okay? And noted physicist Roger Penrose here said what Minkowski did was take relativity out of the special theory of relativity and present us with an absolute picture of spatiotemporal activity. In other words, an objective geometry that does not depend on any observer. What was Einstein's reaction? Well, he was working at the Patent Office this time, and he was asked to write a review of special relativity. He heard about this on Perkins Observatory thought. Now, what a review is basically it's a summarization of the topic of scientific research in the case special relativity and all the work that had been done on it up to that time. That's what made it so talking about Mr. Mikowski in the work.
Bruce.
And he strongly disagreed. Whether or not his relationship with Mikowski played into that, hard to tell, but he didn't like the idea. He called it superfluous learning.
That's the time.
It's in German. I couldn't even pronounce it. Will because all the pronounce it.
Right.
Right. It's a devastating insult. Right. But he continued to work on his review. And as he worked, he continued to be troubled with the conflict of his work and Newton's work with special relativity. So let's look more at what is going on. Soon he realized that special relativity was really inconsistent with Newtonian gravity. Okay? And one of the reasons is because of the way Newton treated mass. He called mass a quantity of matter. That's all he addressed it as a quantity of matter. And you recall Einstein's work with energy. All forms of energy should be included with mass because they're quantities. And Einstein basically said, upon this, it was most unsatisfactory to me that although the relationship between inertia and energy is so beautifully derived in special relativity, there is no relationship between inertia and weight. So what this comes down to is Newton's principle of equivalence. Okay, let's take a look at what's going on here with that. Right, there are two contexts for mass in Newton's theorem. Okay? And they are inertial mass, which related to momentum, how difficult it is to get a piece of matter moving. In other words, how resistive it is to the motion in general. And then there's, we call it passive mass. And there's gravitational mass. Right? And we'll call that active mass. And it has to do with how one part of the piece of matter behaves around another piece of matter. Okay? Newton argued these were the same. How? Well, let's look at Newton's second law. And here against force equals mass times acceleration. Proportionality constant here is inertial mass. Okay, it's basically the mass that's in motion. Okay? We can rearrange this equation and put the acceleration on one side and force divided by the inertial mass on the other. So we've rewritten Newton's laws. We can define that as gravitational acceleration. Okay? And so we've rewritten it, and we can also incorporate Newton's laws of gravitation here to help us define this new constant. And so we relate the active and passive masses together via the third law. In other words, we set the second law equal to the law of gravitation. Using the third law, we find that the ratio of the active mass and the passive mass are equivalent for each object. Okay? Newton appealed to Galileo's work to show they were equivalent. Okay? But are they really? Well, Newton found that they are equivalent to about 1 in 10,000. Modern value puts it about 1 in 10 to the 13. Okay? But Einstein thought this idea was ad hoc. Right? Newton was actually, by the way, displeased by his theory of gravity. He said in a letter that gravity should be innate, inherent, and essential to man, so that one body can act on another at a distance through a vacuum without mediation of anything else is to me so great an absurdity that I believe no man who has his philosophical matters has in his philosophical a competent faculty of thinking can ever fall into it. So, in other words, he expressed discomfort with his axiomatic distance idea of gravity. That an object can exert a force on another for a distance, nothing in between them. But yet, this is a fundamental aspect of his law of gravitation. And there's one more issue with Newton's gravity. There's no dependence on time. It's instantaneous. And that's definitely a problem. So, recall that Einstein had expanded the equivalence principle here. And basically he's working on a way to use it to preserve the laws of physics in all situations. So, and what did he achieve in his initial 1905 work? Okay, you'll recall the laws of physics are the same in all frames. The inertial frame means no acceleration. Okay, there's a problem here. Gravity produces the acceleration. It's non-inertial. Okay? So, you can't get rid of it. It's always there. It's not abolished. So Einstein was left with the question, how relevant is the principle of relativity in this case? He needed to generalize his theory to include gravity. So, a little bit more, just real quick, on that 1907 review paper he was writing. It's offered a comprehensive review relatively 2 years after its initial introduction. It also contained Einstein's, the first time he mentioned gravitation, the ideas he was having, including the principle of equivalence, where he proposed the physical equivalence of gravitational field and an accelerated reference frame. And based on these principles, he predicted gravitational time dilation and redshift, and attempted to predict the bending of light. And so it was around this time as well that Einstein had what he said was the happiest thought of his life. If a person is falling, they do not feel their own weight. So in other words, a free falling frame is inertial. With this realization, he set out to modify Newton's principle of equivalence. How exactly? By a thought experiment. So let's look at some of these in a more modern context. What are these thought experiments? First one here, let's imagine two situations, okay? First, I have an observer and a rocket. He's holding a ball. And they're in deep space, as far away from anything as they could possibly be. Second, we have an observer in an elevator here on Earth. Okay, the elevator's sitting there and locked in place. Okay, neither have windows to see the outside world. It's an important point. Let's set the rocket accelerating. And we'll accelerate at 1 g, the equivalent of 1 Earth's gravity, at about 10 liters per second. When he releases the ball, ball falls towards the back of the rock, the opposite way the acceleration is going. And when the observer in the elevator releases his ball, the same thing occurs. It falls to the floor. Now let's look at a second thought experiment. We've got our observer in deep space, but this time we don't set up the rockets. And again, we have the observer in an elevator here in Earth's gravitational field. Okay, this time we let the gravity or the elevator fall under gravity. And he releases the ball simultaneously. When he does, he observes the exact same thing the person in the rocket there observes. The ball makes and staying stationary and melted to where it's released. And this led to Einstein's version of the principle of equivalence. By no experiment can an observer tell the difference between an acceleration and being present in a gravitational field. So regardless of what I do, I'm not going to be able to tell the difference.
Sure.
Let's look at another version of the thought experiment. Instead of a ball, we're going to use a particle like a photon. Okay, and I'm going to release it from the detector there on the floor, fire it towards the ceiling. I'm going to leave the rocket stationary. And so the detector then receives the photon. And it's the exact same wavelength I release it. Do the same thing in the elevator when I drop it. Observe the exact same wavelength of photon as I release it. Let's repeat the experiment though. And this time we accelerate the rocket. Fire up the photon, and I actually measure a photon that has longer wavelength.
I'm good.
Same as if I'm stationary in an elevator on Earth. I will measure a longer wavelength than my shot off. They are the exact same wavelength, in fact. So, in other words, this experiment, I could not tell if I was on a rocket ship traveling through space or if I was on Earth. So what are the consequences of this? Well, you can think of the peaks of the waves of a photon as like a clock. As each peak passes, it's like a tick of the clock. Okay? And so longer wavelength means there'll be a longer interval between the ticks of the clock. Okay? So here I plug in a gravitational field into Minkowski's metric here. And this actually predicts time dilation and redshift by gravity. Now, also, we'll see light will be deflected by gravity. When I shoot off a particle, if I have a laser here, if I fire it here, all right, if I could hold this precisely and measure very precisely, the spot would actually be lower to this point where I emit the beam of light because of Earth's gravitational field. In fact, this is, again, not another new idea. All right? Light reflected by gravity was actually predicted by Newton. He wrote, "Do not bodies act upon the light at a distance, and by their action bend its rays? And it is not this action strongest at the least distance." It's from his book on optics in 1687. So even though he thought of it, he didn't calculate it. Actually, it came down to this guy in the early 1900s or 1800s, a German astronomer, Solmer here. He calculated it, and he found it to be about, by the sun, by the way, measuring light from a distant star by the sun coming to the Earth, to be about 0.84 seconds in the arc. They're very small. So now Einstein, he didn't pursue this idea further until much later. He took a break basically from revolutionizing mechanics to revolutionize a different branch of physics with his theory of specific heat, which helped form the foundation of the quantum theory of matter. It was not until 1911 that Einstein returned to gravity. Okay. And he set out to determine how much gravity deflects light and why it does so. So if you recall, in his equivalence principle with energy and mass, essentially by this light has a weight. It should be deflected by gravity. Okay? And so he set about calculating it. Started off with Newton's theory. And he came up with a slightly different value, 0.3 seconds in the arc. And that's what he published. But he kept working on the problem, wasn't satisfied. Because he soon realized that not only would gravity affect time, it should affect space. So here's another thought experiment. Consider a circular platform here. And we place rigid rods along its radius, and then place them along its circumference. And then we set it rotating rapidly. The rods along the circumference will experience relativistic light interaction, but the rods along the radius will not. And so what this means is that you'll get different value for pi. Therefore, geometry is not Euclidean in a rotating flight. So how do you reconcile this with special relativity? This is when the idea of curved space started coming to Einstein's mind. And so the question, how does he do this and make it consistent with theory of relativity and also in Newton's laws? So, and it must be a way that all observers agree with what they observe. Okay? So this, only then did he understand what Minkowski had proposed and appreciate it for what it was. It was only then, unfortunately, Minkowski had died soon after the 1907 conference, and so there was not a chance to reconcile between it. But with Minkowski's work in mind, he set about formulating a more general theory. But first, to formulate his ideas, he needed some math help. He didn't have the mathematical skills to do this. And so he reached out to an old classmate, Grossman, for some help. So what exactly did he need? You need a 4D generalization of a 2D cold manifold. When you see the word manifold, think space, just the mathematical term for space. Grossman said, well, this has already been done and to infinite number of dimensions, called the Riemann manifolds. These were derived in the 1850s. But there's still this requirement. In other words, all observers must agree on laws of physics.
Okay.
So let's look at Minkowski's space-time interval again. Recall, again, this is what's called pseudo-Euclidean. And we can also rewrite Minkowski's metric as follows, as derivatives. And we can introduce that a weak gravitational field. When we do so, they've modified the space-time interval,
Cool.
and it shows that gravity modifies the geometry of space-time. And we can see that in the absence of gravity. In other words, we set this term to 0, we get back the original metric, the Minkowski metric, and thus the laws of physics are preserved. And so, in other words, there's not going to be any accelerations. So, when gravity is introduced, light and objects do not follow a straight line, now they follow something called a geodesic path, or a curved path. It's like on the surface of the Earth. And they experience an acceleration. Einstein basically then formulated this equation. And this term here is the acceleration term. All right, and this is the apparent acceleration is fictitious, like the Coriolis force or the centrifugal force. Okay? So here's an example of the Coriolis force. It's also what causes hurricanes to spin up. Okay? It's driven by the Earth's rotation. All right, you also need to count this, if you're doing long-range artillery, things like that, you have to account for the rotation of the defense ballistics. But wait a minute, I said fictitious. Wait a minute. These forces are real, and sometimes they have hilarious effects. Again, the word fictitious here means a theoretical construct that does not mean fake. So in 1912, he put forward his new equivalence principle. This is now called the strong equivalence principle. And let's recall Newton's first law. And then let's rewrite it. And this is the rewritten form. There exists a standard motion that bodies follow when all forces except for gravity are abolished. The standard motion is called free fall along a geodesic in space-time. So this is the strong equivalence principle. With his friend, they collaborated on a paper in 1913. Grosvenor wrote the parts on geometry. Einstein wrote the parts on gravitation. He was pretty unsuccessful. It would take a further 3 years for him to formulate general relativity. In the meantime, with the work that was out there, he was decided to put it to the test. That's what you do. You put an idea out there in science, and you put it to a test, see if it actually is true. And so in 1914, there was an eclipse that was going to happen in Crimea, Crimean Peninsula, in modern day Ukraine. And there was an expedition led by, this is Erwin Finley Freundlich on the left and William Wallace Campbell on the right. However, there was a complication. The outbreak of World War I. Finley here was jailed.
Go. Right.
Campbell was allowed to continue. However, they were clotted out. They get to make the measurement. But this was lucky for Einstein. Okay, why was it lucky for Einstein? Well, let's get back to that. He was in the process of constructing general relativity still. And as work continued, eventually he learned the mathematics and formulated his new theory of gravity. And it resulted in his famous field equations. Now, I use the plural here on purpose. You know, it looks like you know that's actually 16 equations.
Wait, one.
All right, it's going to what's called Einstein notation. It can be simplified to 10 if you use symmetry. And symmetry is your friend in physics. Finding and using symmetry can simplify problems greatly. In any case, all these equations will reduce to Newton's theories in simple situations, which is again something desirable. I forgot for punishment, here's what they look like expanded within equations. All right, and then ignore this term here in the meantime. Hopefully have time to get to that later. But if we expand in normal notation, I said it's written in Einstein's notation too, but this is normal notation using summations, that's what they look like. And if I just take this first term here and expand it out, it looks like that. So you can see why it took a while to derive mathematically this theory. Quite complicated. But basically what it shows us is that space tells mass how to move, and mass tells space how to bend. That's what this equation tells us. And with it, one of the first things they will do is successfully calculate the perigee relationship of Mercury. Mercury's orbit, for some reason, would not be exactly where it was predicted to be due to its laws. Einstein was able to successfully predict the orbit of Mercury.
Nice.
And he decided to recalculate the bending of light based on his new theory. And
Good.
what he found was that his solution was twice what Newton's was.
Like. One.
So in fact, with Newton's equations found it was 0.83, he found 1.77 arcseconds. So, and if he not taught this, and instead, if they had observed the 1914 eclipse and measured 1.7, it would have looked like Einstein was retroactively came back and correcting his work, and now they were in his reputation up in the history. So that cloudy day saved his career. So finally, in November 1915, his theory was published. And this is him time of the publication, and he went on to say, scarcely anyone who fully understands this theory can escape from its magic. Now, as an aside, so here, David Herbert, he actually derived those equations 5 days before Einstein did. However, he who publishes first gets the credit. And Herbert wanted them to call them the Einstein Herbert. Good, waiting, side, hidden. He who publishes first.
Sweet.
So, we jump ahead to 1919, and there's yet another eclipse. But again, put this to the test. This expedition was led by Sir Arthur Eddington and Sir Frank Watson. Dyson. They went to an island off the coast of Africa. This is one of the photographs they took. It's hard to see, but they basically measured the position of stars here during the eclipse, and they compared it to a plate taken earlier with the star's position measured. Okay? Now, there was some debate of the validity of this measurement, but later measurements made during other eclipses confirmed the value of 1.7 arcseconds. And What Eddington actually could find out was the principle of equivalence. Now, Dyson at the Royal Society meeting said, when they made this announcement, after careful study of the plates, oh, by the way, that's what they measured. A little bit less, but within the errors, it was the 1.7 on the sun. Dyson said when presenting these results that after careful study of the plates, I compared to say that they confirm Einstein's predictions. A very definite result has been obtained that light is deflected in accordance to Einstein's law of gravitation. Now, Einstein said to his assistant when she read the telegram he had received about the successful confirmation of his theory and asked what would happen if he had been wrong, he basically said, it would have been too bad for nature.
Bam.
With this confirmation, fame. Here's an example of a headline from the time. New theory of the universe. Newton's ideas overgrown. Not entirely true. It's over the top. Lights all askew in the heavens. Men of science and more or less agog over the results of the eclipse observations. Einstein theory triumphs.
So,
And his fame precipitates course to this day. He was honored by even the rock band Queen. They have a song called 39 that basically talks about the theory of relativity, particularly special relativity, but it's a very good song. You should listen to it. And in 1921, he got to take part in the ticker tape parade in New York. He's the only scientist to ever have been accorded this honor. Following year, he won the Nobel Prize, but probably not for relativity. He won it for the discovery of the photoelectric effect. He never won a prize for relativity.
let's go again.
And so we come full circle back to 1933, the Trinity College, and now we see what all the fuss is about. General relativity, I'm sometimes asked, what's the utility of it? Why is it so important? Well, it's useful in cosmology, to understand the structure and formation of the universe, gravitational lensing of stars, studying again of light, in distant galaxies, collapsed objects, black holes, neutrons, stars, light and warps, and most importantly, in modern GPS. Without it, you would not be able to accurately find where you're going or where you are on your surface. Without general relativity, it would have a resolution of about a mile or so. You would not know you were within time. That's totally useless from that view. So at this point, I'll leave it up to the audience. I can continue, talk a bit about gravitational waves, or if you guys are had enough, we can call it quits, but it's up to you. Shall I continue?
Sure.
Okay.
Sure.
So Tom, what about gravitational waves? My goodness. All right, well, let's talk about what are gravitational waves. And they're basically ripples in the fabric of space and time itself. Okay? And it's caused by the acceleration of objects. All right? You see here, I'll talk a bit about this more in a moment. It's the merging of two objects, two black holes. And this is in the process of generating gravitational waves as they orbit. That's an acceleration. Eventually, when they merge, that point they merge, and then they'll send out a large amount of more gravitational waves. And they can be polarized. They can have a direction to them. Now, as I mentioned, it's with accelerated bodies. Things traveling at a constant velocity do not generate gravitational waves. So, quick on Einstein again, was this really his idea? Well, the idea actually goes back to 1893. This same Heaviside noted that the inverse square relationship between gravity and electromagnetism those look almost identical. And as electromagnetic radiation propagates through space with waves, so should gravity. So like Newton's gravitational law, and that's Coulomb's law, like there. To both anti-gravity. In 1904, Poincaré proposed that gravity waves should be emitted from a moving mass and propagate at the speed of light. Einstein was skeptical about this, though, in part because there were no gravitational dipoles. What does that mean? Like electric charges, you have a positive and negative charge. There is no positive and negative gravity. Gravity is only negative. It draws things in. There's no repulsive gravity or no anti-gravity. So he published this though before special general relativity was put forward. But Einstein heard of them and dismissed them. In fact, he went on to publish a paper in 1936, cast doubt on the existence of gravitational waves, and then at a conference in Chapel Hill, North Carolina, this is Richard Feynman here, the first gravitational wave conference, or general relativity conference, I'm sorry, the discussion of gravity waves came up. Young Richard Feynman, he attended that conference. First actual attempt to measure them was in 1969 by Joseph Weber, his engineer, who became interested in gravitational wave. So his apparatus basically consisted of a large solid aluminum cylinder that he basically put sensors around that would detect the flexing of the aluminum cylinder via what's called a piezoelectric effect. The flexing of it would generate a small electric current that could be kept good. He claimed he had detected gravitational waves coming from the sun of the Milky Way. However, it was later found to be erroneous because he didn't know any thermal effects. He could control the temperature thermal expansion of the cylinder. And this continued to feed into the skepticism. That is until 1974, when the first binary pulsars were discovered. And when they measured the shift in their orbits and the timing of the pulses, it was consistent with the prediction of general relativity and the existence of gravitational waves. So in other words, each orbit, the system was losing energy, and so they would spiral in closer and closer together each orbit. And so how, in the end, do we actually detect gravitational waves? That's, of course, with waves. So there are two experiments. Yeah. The LIGO experiment and the Virgo experiment. LIGO are two detectors out in the United States. They're very large L-shaped detectors. Basically, they're large vacuum tubes, very, very long tubes. As they evacuate the air, they put mirrors of either end and fire lasers down both of these. They're L-shaped, so that way they get many axis direction detection. Virgo is located in Italy, which is from the Thailand, was the European experiment. And they use laser interferometers. This has been set up, and they bounce back and forth between the mirrors, and they set up what's called an interference counter. And when the links of the tubes stretch and compress, these are going to go out of phase. And they can measure that. And so the first successful detection was in 2015, almost 100 years after his publishing in General Relativity. Einstein's published in General Relativity. And what was discovered were a pair of binary black holes. Here's the
Yeah.
and then they translated the sound and increased the pitch. So what you're hearing are the final orbits, and then
Good for something you merge together.
the first detection, one of the black holes was 36 times the mass of the sun, the second one was 29 times the mass of the sun, plus or minus a certain amount. However, you add that up, when they merge, they formed a black hole of 62 times the mass of the sun. How could you add that up? It's more than 62 times. So what happened to that extra 3 solar masses? Well, you remember E is mc squared.
Right.
Part of it was converted into the energy that you get the gravitational waves. So, I got a little demo here I'm going to do. I wrote something in a book called Python that will simulate some of these detections. And there it is.
Okay.
And so what I'll do is I'll input, let's just simple values, a typical solar mass black hole, pre-solar mass black hole, and 2 of them, and let's collide them, see what we get.
Oops.
We're on the wrong screen. So, first what we get is this.
Yeah.
Okay, so explain what we got here. These are the initial conditions. I put in 2 pre-solar mass black holes. I didn't give them any spin or spin angles or anything like that. And I did not give them any different orbital inclination. Put them at 100 parsecs, megaparsecs away. That's the galaxy, say, out at Herman cluster. This was their initial orbital period. An initial separation, which is about 2 years, or no, I'm sorry, 2 days. Or no, less than a day, I'm sorry, 2 hours. And their final orbital period merger was about 0.002 seconds. So they were going quite a significant fraction of the speed of light when they merged. And basically the results again, and even though they were 3 solar masses, it was not total 6 solar masses. Right, some of the energy is converted to gravitational waves here. Okay? And you're not going to scale these waves. The simulation I showed earlier was a little deceptive. Okay, the wavelengths these waves are actually very long, and but the change, how much they flex and stretch these arcs, is very, very small. In this case, it's about 10 to the minus 13 meters. Very, 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 very small, a little bit bigger than an atom, basically. Is the amount that the entire Earth, its diameter changed as these gravitational layers went by. So you would not have noticed. Okay? And then here's the plots. Here shows the important physics going on. This is the frequency, and as they near merger, the frequency gets higher. It's like you heard there in the light of data. Okay. And this gravitational wave training, that's how much the flexing is. And the maximum flexing occurs right as you approach merger. But again, it's only going to be like a fraction of an atom that this will occur. Because it occurs at that distance. Okay? If I put in let's do this. Now, let's do this. Everybody just move on. So, the key thing about, we go back to our talk here. Let's spare gas. So the other key things to point out is, by the way, I'll mention the first neutron-neutron star binary merger was in 2017, 2 years later. This turned out to be an important event because most of the elements on the periodic table you are familiar with, like gold, silver, things like that, are made in these mergers. Right? They would not exist without these mergers. Okay? Oh, here's a plot of several, and I skipped this. All right. Here's the detections until 2023. Basically shows the resulting combined massively black holes. I won't go into a lot of detail. Let's be showed here. People can ask questions afterwards if they want of it. But there have been thousands of detections now up to this point. So what's the future? This may have been asked with the recent budget changes and things like that coming out of the administration. There was a mission called LISA that was going to have a system of satellites out in space, and these were going to be separated by millions of miles, have lasers firing between them, and it has very, very long wavelength gravitational waves they pass by. That's what this is designed to detect. They're mainly looking for what are called primordial gravitational waves from the Big Bang itself in the early universe, or it's an merger of very, very large black holes. Turns out there's a certain range of black holes that can be detected, black hole mergers with light that can be detected. If they're too small or too big, they can't be detected because of the size of the detector of LIGO and Virgo. So they wanted to build this much larger one to look for these primordial gravitational waves. To what's playing maybe in the 2030s, but probably not going to happen. And thus,
Gravity. It's a wondering.
Any questions? Thanks, yes,
The original detection slider, did they know exactly what it was? Well, where's the black hole?
no.
Have an idea to
The reason they have, one detector will at least tell you there's been a gravitational wave of that sun. Having two separated by distance, you can look at the timings. Two will give you like a region in the sky. 3 narrows it down even more. But still, they need now better detectors and more of them to really zero in. We've been lucky though, because there have been detections by other telescopes that, in case the electron star mergers, it generates what's called a hyperneutron, which generates more visible light. So there was a visible detection to that simultaneous to the tiny interpretational wave of that. And so that's why they were able to piece that together. So it has to be detectable to form it, narrow down to where it is in the sky, actually do other observations. There's got to be another type of detection, gamma rays, X-rays, optical things that already. So, other question?
So some of that mass that disappeared in the merger was the light and gamma rays.
Some of it was turned into light, most of it though was put in, generates the gravitational wave themselves.
So what do you need mass? With the solar mass getting less and less and less as it gets closer. But it is generating waves all the way something. But it's not something that is a conversion, but it's something that is up.
Right, it leads off.
Any like call it to bigger parts.
Right. Yeah, that simulation I would go to the back to it shows is that when they actually merge, you'll see as the simulation runs, they.
What's wrong?
I'm sorry, wrong slide.
Not. Good. But too far.
There we go. You actually will notice that they don't just kind of skim each other and merge. They get to a point and then they just like eat together. All right. So watch close. Here they at. What you're seeing at the bottom, this is called the gravitational potential plot. It shows basically the gravitational field in 2 dimensions. Okay? And as you see, as their potential merge, right, this is the point here where the actual merger occurs. There. Right? They just suddenly loop together.
So the speed of rotation is continuing like fast.
Yes.
And the result is the amount of weight being produced increases as a result.
Yes.
Because it's producing waves all along and split the dimension of the total.
Yep, exactly. Yep. And then in the end, you get what's called a breakdown. When it finally merger, the space basically kind of springs back a little bit and creates what's called a breakdown. And from that breakdown is the part of how they are able to determine the final mass.
So are these events common enough that arguably were being bombarded by gravitational waves?
Yeah. Yeah, yeah, basically, they had daily rates of how local universe, like what the observable universe.
You say it will affect in the Big Bang itself?
What's that?
And the effect from the Big Bang itself?
Well, again, those have been, part of the problem is that space is expanding. And that expansion stretches those waves. And so they're very, very, very long wave, and that's why they have to build these the satellites to come millions of miles apart. I mean, all they have to be able to measure these very long waves of gravitation.
I mean, still be there, it's just detectable with the equipment. That we
Yeah.
Another question. Big Man. But I think days at a start, and then they migrate out from the source.
You want that?
In particular, like particular cycle, the whole cycle rate moves out by itself. It doesn't occur at a certain time. You only occur in as it hits you. So that rate is gone.
Right.
And that's what comes along. So if we have a big bang wave time along, and that wave has gone, and it's actually sugar before.
But you have to remember that universe is actually in zones.
Well, it's still there. We're not out far into like.
Right, but there are places that are far away that light and information is still coming to us that hasn't arrived for us. So those primordial back they're there in the back. It's like a background radiation.
There it is, without radiation, and it's still intact.
Yeah. So.
In fact, they call it gravitational backstop.
So there's that type rating.
It's so hard.
Yes. I remember a long time ago, it's like back in the 50s, you know, giving away my age, you know, but I remember, this is going back to when we were talking about the laws of force and motion of Isaac Newton, you know, and I remember Dr. Lee Force rightly saying that man will never go to the moon because the rocket never comes in the absence of when an atlas begins.
They like you.
That really remember.
Having a fundamental misunderstanding of Newton's laws.
And the rockets.
Yeah, it's basic. Yeah, it's thinking that rockets need something to push against to work. They don't. At least not the way he thinks.
For rockets, you need oxygen, right? So it's about.
So they carry oxidizer with them.
Yeah, it's self-contained.
Yeah, and the fuel. But what happens is in the combustion chamber, right? The exhaust is pushing against the rocket. That's what pushes it going forward. That's Newton's third law. Like reaction, there's a positive reaction. So it's basically what's going on in that nozzle. That's what's pushing the rocket.
Right.
Questions? All right.